All right, ladies and gentlemen, in today's video we're going to be looking at section 11.1 on sequences and their notations. In fact, I'm currently teaching Calculus 2 this semester as well, and in Calculus 2 we're actually making use of all of the material that you learn in this chapter on sequences and their notations. And in fact, we do repeat some of the teachings that you learn in pre-calculus again in Calculus 2. So this will not be the last time you see sequences and their notations for sure. They play a very prominent role in second semester calculus. Let's start with a definition. A sequence is an ordered set of numbers. Now that's one definition of a sequence. So for example, a sequence could look like 1, 3, 9, 27, 81, and so on. And this three dots here called the ellipsis simply would mean in this case that this sequence runs on forever in a consistent pattern that we've already established for the numbers. Okay? If I didn't have the ellipsis here and I stopped, that would be a finite sequence instead of this infinite sequence that we're seeing here. Now, another way to describe a sequence, another definition, which we will find actually more useful. A sequence is a function whose domain is from the counting numbers. So you know the counting numbers, 0, 1, 2, 3, 4, and so on. Any subset of those counting numbers could serve as the domain for a function to define a sequence. Now, relative to the sequence, this ordered set of numbers here, I could define this ordered set of numbers, therefore, by this function. 3 to the n minus 1, where n goes from 1, 2, 3 onward. So look at how that works. When n is equal to 1, 3 to the 1 minus 1 is 3 to the 0, gives you 1, the first number. When n is 2, 3 to the 2 minus 1 is 3 to the 1, gives you 3, the second number. When n is 3, 3 to the 3 minus 1 is 3 squared, which is 9, the third number, and so on. So these are just two different ways, the function representation of the sequence and the listing of the numbers in order to represent the sequence. Two ways to represent this sequence. And again, this functional form is generally what we find much more useful from a pre-calculus and a calculus point of view, because we are a function-based study in these topics, right? We study functions in pre-calculus and calculus. All right, let's take a look at a couple of examples from the exercises. Problem number 6. You're given this sequence whose generating function is 2 to the n minus 2. And you're asked to write down the first 4 terms of this sequence. So we're going to assume that we're starting with n equals 1 as we write this. So a sub 1, 2 to the 1 minus 2. That's 2 minus 2 is 0. A sub 2, n is 2. 2 squared minus 2, that's 4 minus 2 is 2. A sub 3, 2 to the 3 power minus 2. 2 cubed is 8 minus 2 is 6. And a sub 4, when n is 4, 2 to the 4th minus 2, that's 16 minus 2 is 14. So this is the first 4 terms, 0, 2, 6, 14 of this sequence. Okay? All right, let's take a look at problem number 8, doing the same type of exercise. You're given the generating function for the sequence to be the negative of negative 5 to the n minus 1 power. So when n equals 1, the a sub 1 term, in other words, is negative 5 to the 1 minus 1. Well, 1 minus 1 is 0. Negative 5 to the 0 is 1. There's a negative in front of that 1, so there's your first term. a sub 2, negative of negative 5 to the 2 minus 1. This power is now 1. Negative 5 to the 1 is negative 5. You negate that, you get 5. A sub 3, negative 5 to the 3 minus 1. That's a power of 2. Negative 5 squared is 25. You put the negative in front of it. There's your third term. A sub 4, negative of negative 5 to the 4 minus 1. That's negative 5 to the third power, which is negative 125, with a negative in front of it, making it 125. So the first four terms of this sequence are negative 1, 5, negative 25, and 125. Okay. All right, let's try a piecewise defined sequence. So in 20, the generating function is given in two pieces. It's either 4 times n squared minus 2 if n is less than or equal to 3 or n is bigger than 6. Otherwise, it's n squared minus 2 over 4. And that again is if n is between negative 3 and 6 in value. Okay? And we want to write down the first 8 terms now. So a sub 1. That, of course, n is 1 is in less than or equal to 3, so we're using this. 4 times 1 squared minus 2. That's a 4 times a minus 1, or a negative 4. A sub 2. 2 is still less than or equal to 3. We're using this rule for evaluating the function. 4 minus 2 is 2, times 4 is 8. A sub 3. Less than or equal to 3 still. 3 squared minus 2 times 4. 9 minus 2 is 7, times 4 is 28. There's your third term. A sub 4. Okay, now the n is 4. That's bigger than 3. So now this is the rule we have to use. Right? When n is bigger than 3 or less than or equal to 6, specifically 4 in this case, use this rule. 16 minus 2 is 14 divided by 4. A sub 5. 5 is still between 3 and 6. Use this rule. 25 minus 2 is 23 over the 4. A sub 6. Again, n is less than or equal to 6. Use this rule. 36 minus 2 is 34 over 4. Now, a sub 7. Well, 7 is bigger than 6. We go back to this rule here. 49 minus 2 is 47 times 4. So let's see, 47 times 4, 45 times 4 would be 180. 2 times 4 is 8, so 188. And a sub 8. 8 is bigger than 6. Use this rule. 4 times 8 squared minus 2. 64 minus 2 is 62 times 4. Well, 60 times 4 is 240. 2 times 4 is 8. 248. There's the first 8 terms of this sequence. Okay? All right. Now, sometimes you're asked, given a sequence, can you write that function? Sometimes they'll say, let's write a formula for the sequence. Okay, so let's try this from problem number 24, where the prompt says, for the following exercises, write an explicit formula for the sequence. This is the sequence. 0, 1 minus e to the 1 over 1 plus e squared. Next term, 1 minus e to the 2 over 1 plus e cubed. Next, 1 minus e cubed over 1 plus e to the 4th. Next, 1 minus e to the 4th over 1 plus e to the 5th. And that's all they give us. That's more than enough for us to see the pattern here. Again, what we want to know is, what is the formula that generates this? Okay? Well, you start here. Okay? When n is 1, n is 2, n is 3, n is 4, n is 5. These are what you're supposed to be generating. So the denominator is easy, right? 1 plus e to the n, 1 plus e to the n, 1 plus e to the n. That part is easy. up top, 1 minus e to the 1 less than n each time, right? So that. And then just double check when n is 1, 1 minus 1 is 0, e to the 0 is 1, 1 minus 1 is 0. You're getting 0 for the very first term. There is your generating function, or your formula for the sequence. Okay? All right, now we also want to show you another way we can define sequences, and this is called recursively defined sequences. Now, recursively defined sequences can be very handy in the sense that it's easy to understand how to create them in terms of a mathematical model. There's some logic to how we actually write the sequence recursively that is sort of natural from the physical world. But from our mathematical point of view, a recursively defined sequence is not easy to work with. Therefore, once we've defined the recursively defined sequence, maybe for some natural physical phenomenon, what we immediately will want to know is how can I rewrite that so that I can actually generate a function like this, for example, that would actually define that sequence. Okay? So again, recursively defined sequences are great for modeling, for understanding physically what's going on in a process. But once you've got that understood, you want to be able to come up with this functional form afterward. Okay? So for now, let's just define the recursively defined sequence. As a recursively defined sequence is a sequence that defines each term using preceding terms. So for example, we could say this. Suppose you're given that the very first term, and we always have to give you a first term to start with, okay, or some value known. And then we can give you this, a rule that the nth term is going to be generated by taking 3 times the term prior to that and then adding 1 to it. And that's the rule you use for n bigger than or equal to 2. In other words, not for the first. Okay? And these two, the initial condition and this part here, the recurrence relation, together define the recursively defined function. Okay, so let's see what this would look like if I were to write out some terms. Of course, the first term that was given to us is 2. What would the second term be? Well, a sub 2, when n is 2, that's 3 times a to the 2 minus 1 plus 1. 2 minus 1 is 1, so that's 3 times a1 plus 1. And we know the value of a1 already. It's 2. So from the previous term, from the preceding terms, we figure out what this term is going to be. 3 times 2 plus 1, and I get 7. Now what about a sub 3? Well, the rule says a sub 3 would be 3 times a to the 3 minus 1 plus 1. But 3 minus 1 is 2. We know the value of a squared. It's the preceding term, 7. 21 plus 1 gives me 22. And so you get the idea that the next term, a sub 4, 3 times a to the 4 minus 1 plus 1. That's 3a cubed plus 1. But take this, 3 times 22 plus 1, that's 66 plus 1, or 67. And you can keep doing this forever. Okay? Now the drawback for this is, compared to up here, suppose I have a sub n as this formula, and I say, okay, what's the 100th term? Well, that's 1 minus e to the 100 minus 1 over 1 plus e to the 100, right? So 1 minus e to the 99 over 1 plus e to the 100. There's the 100th term of that sequence. What if I asked you what a to the 100 sub 100 is here? Well, it's 3 times a to the 99 plus 1. So now you need to know a to the 99. So you'd have to go back and find a to the 99. Well, that's 3 times a to the 98th plus 1. I don't know a to the 98th, so I have to go back and find that. And you have to go back all the way down to a1. many, many, many steps, 100 steps back, to figure out what a to the 100 is, as opposed to with a formula, just plugging in directly and knowing what that term is. And that's the major advantage to the formula approach to this, as opposed to the recursive definition approach. Again, the formula, you can get directly the value of any term by plugging in. The recursive, you can't, but the recursive has this nice natural understanding of how the next generation is created from the prior generation. This recurrence relation can have a natural physical understanding to it that helps us. Okay? All right, so let's take a look at a couple of exercises now. In problem number 26, the author asks you to write the first 5 terms of the sequence, and he gives you a recursively defined function to practice with. So 26, write the first 5 terms, where the first term is 9, so we got that one already, and the nth term is the n minus 1 term plus n. So that means I have to come up with the second term. Well, the second term is going to be the previous term plus n, where n is 2. So that is 9 plus 2 is 11. There's a sub 2. A sub 3, the rule is that's a sub 2 plus 3. So 11 plus 3 is 14. A sub 4 is a sub 3 plus the n, which is 4 now. 14 plus 4, I get 18. And a sub 5, that's a sub 4 plus the n of 5. That's 18 plus 5 is 23. So the first 5 terms of the sequence are those values right there. Okay? Do one more example of that. Number 28. A sub 1 is negative 4. A sub n, the recurrence relation, is it's a to the sub n minus 1 plus 2n divided by a sub n minus 1 minus 1. So of course there's the first term of the sequence. A sub 2 is going to be a1 plus 2 times 2 divided by a1 minus 1. So that's a negative 4 plus 4 over a negative 4 minus 1. A 0 over negative 5 is 0. There's your second term. A sub 3 is a sub 2 plus 2 times 3 over a sub 2 minus 1. Remember, 2 times n is the form where 3 now is n. So that's 0 plus 6 over 0 minus 1, negative 6. There's my third term. A sub 4, that's a sub 3 plus 2 times 4 for a sub 3 minus 1. So that's a negative 6 plus 8 over negative 6 minus 1. That's a 2 over negative 7. There's my fourth term. And a sub 5, a sub 4 plus 2 times 5 over a sub 4 minus 1. So that's going to be a negative 2 sevenths plus 10 over a negative 2 sevenths minus 1. So let's see what that is. Let's see, that's 70 over 7 minus 2 over 7 is 68 over 7. And this is going to be a negative 2 sevenths minus a 7 sevenths is negative 9 sevenths. So negative 68 over 9. There's your fifth term. Okay? All right. Let's take a look at problem number 34, where they ask us to figure out what is the recursive formula for the sequence that they give us. So in 34, the sequence they're giving us is negative 2.5, negative 5, negative 10, negative 20, negative 40, and on and on. And so when I look at this, I realize that the first term, of course, is negative 2.5, and that the relation is that when I get from here to here, all I'm doing is doubling. Double, 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 double. In other words, to get the next term, you just multiply the previous term by 2. And there's the recurrence relation defined. And of course, you plug in and check to make sure that it works, but that is a pretty straightforward problem. 36, the terms are 2, 4, 12, 48, 240, dot, dot, dot. A sub 1 is 2. Now, what is the relation here? What did I do here? I took the previous term and multiplied it by 2 to get this. Then I took the previous term here and multiplied it by 3. I took this previous term, multiplied it by 4 to get this. This times 5 to get this, right? Write the n values. 1, 2, 3, 4, 5. Okay? 2 times 2 gives 4. 3 times 4 gives 12. 4 times 12 gives 48. 5 times 48 gives 240. So all I'm doing is taking n times the previous term to generate the sequence. 38. 15, 3, 3/5, 25ths, 3 over 125th, and on and on. So what am I doing here? Well, the first term is 15, and what am I doing each time? I'm multiplying the previous term by 1/5 to get the next term. So 1/5 a n minus 1 is the generating function, okay? Or is the recursive relation, okay? All right. Now, final thing to show you in this section is this idea of factorial notation. N factorial is the product of all integers from n to 1. For example, 5 factorial is 5 times 4 times 3 times 2 times 1. It's just a shorthand notation for all the whole numbers from this number down to 1 multiplied together. Factors, these are all factors of the product, 120, right? All these are factors of 120. Okay, that's why it's called factorial notation. Or more generally, n factorial is n times n minus 1 times n minus 2 times n minus 3, all the way down, 3, 2, 1. Okay? Now, the interesting thing about this is factorial notation can be very easily defined recursively. We start this way. 0 factorial is 1. That's just part of the definition. Then n factorial is simply n times n minus 1 factorial. And there's your recursive definition for factorial notation. All right, let's take a look at a couple of the exercises involving factorial. Before we do, let me show you on a calculator how we do this evaluation. Okay? So here's my little TI-30 that I borrowed from College of the Mainland. And suppose I wanted to calculate 5 factorial. Well, on this calculator, I enter the 5, and then I have to look for the factorial. Now, some calculators will have a little exclamation point right there for you to use. On this one, it's buried under the PRB menu, and that's where you have NPR, NCR, and the exclamation point. Just toggle over to the exclamation point, hit enter. There's 5 factorial appears, hit enter again, and it'll evaluate it, giving you the 120 that we claimed. Now, the interesting thing about factorials is they grow quickly. 10 factorial is 3,628,800. 20 factorial is 2.43 times 10 to the 18th. So 18 decimal places you have to move to write that number. Okay? Factorials get large. Very quickly. Okay? Now, in fact, on this calculator, where it only allows 2 digits for the powers, right? So, for example, if I do 30 factorial, okay, you may notice here, this is 2.65 times 10 to the 32 power. it can only use 2 digits up there in the power, meaning it can at most go to 10 to the 99th power, or 99 decimal places, so that we have to move this decimal over. Okay, that's the limitations of one of these calculators. Now, some of the graphing calculators will allow 3 decimal places up top, but they're still limited by that. Okay, and on this type of a calculator, the biggest factorial we can compute is 69 factorial. That's 1.71 times 10 to the 98th power. So you have to move that decimal place 98 places to write that number. Excuse me. And if you were to try 70 as the factorial, it would fail. Let me show you what that looks like. 70 factorial, overflow error, because that power is actually now 3 digits instead of 98 like it was. Okay? All right, so that's how we use our calculator to compute some factorials. Now let's do a couple of quick exercises involving factorials from the exercise set. Okay, let's start with problem number 40. In 40, you're asked to simplify this expression or evaluate it. 12 over 6 factorial. Well, you have to do what's in the parentheses first. 12 over 6 is 2. And 2 factorial simply is 2 times 1. And so you get 2. Very easy problem, right? 42. 100 factorial over 99 factorial. Well, here's an example where we cannot use our calculator most of the time to calculate 100 factorial or 99 factorial. So what we have to do is understand what 100 factorial means. Recursively, it means 100 times 99 factorial, doesn't it? And so you'll notice you have a 99 factorial in the top and in the bottom as factors. Those now can cancel. In other words, I don't have to compute all those out, and I just get my result of 100. In 44, we want to write the first 4 terms of the sequence, and now we're going to use factorial notation in the function. So 3 to the n 3 times n factorial over 4 times n factorial. So a sub 1 is going to be 3 times 1 factorial over 4 times 1 factorial. 1 factorial is just 1, so that's 3/4, and there's the first term. A sub 2, 3 times 2 factorial over 4 times 2 factorial. 2 factorial is 2, but of course those just cancel anyways, and you're left with 3/4. This might be a little boring, right? A sub 3, 3 times 3 factorial, 4 times 3 factorial, those cancel, you get 3/4. Right? In fact, you could look at this and say, hey, can't I just simplify that? A sub n is always 3/4, and so that's your term every single time. Okay? 46. A sub n is 100 times n over n times n minus 1 factorial. So again, write the first 4 terms of this. A sub 1, 100 times 1 over 1 times 1 minus 1 factorial. That is 0 factorial there. Remember the definition. 0 factorial is 1. 1 times 1 is 1. So you get 100 over 1. There's your first term. A sub 2, 100 times 2 over 2 times 2 minus 1 factorial. So that's 200 over 2 times 1 of 2. You get 100 again. A sub 3, 100 times 3 over 3 times 3 minus 1 factorial. Okay, of course these 3's, you can think of those as just canceling, can't you? So 100 over 2 factorial. 100 over 2 is 50. A sub 4, 100 times 4 for 4 times 4 minus 1 factorial. That's, again, cancel the 4's. That's 100 over 3 factorial. That's 100 over 6. And there you go. You've got the first 4 terms. Okay? All right. Now let's conclude with one example of graphing one of these functions, okay? So let me use some lined paper for this. Sometimes our graphs come out a little cleaner when we use lined paper. I want to take number 50, and they want us to graph the first 5 terms of the sequence. We're in 50. The sequence is given by recursively a sub 1 is 1, and a sub n is a sub n minus 1 plus 8. So let's generate the first 5. Of course, 1 is the first. A sub 2 is going to be a1 plus 8. That's 1 plus 8 is 9. There's the second. A sub 3 is a sub 2 plus 8. That's 9 plus 8. 17 is our third term. A sub 4 is a sub 3 plus 8. That's 17 plus 8 is 25. There's our fourth term. And a sub 5 is a sub 4 plus 8. 25 plus 8 is 33. So I want to graph this sequence. 1, 9, 17, 25, 33. This is the domain. The domain is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. This has to go from 1 to 33. So how can we do this? There, run it up like that in powers of 4, or multiples of 4, sorry. A1 is 1, so that would be about here. 1/4 of the way up. A sub 2 is 8. Well, 8 is this height. A sub 3 is 17. That's just a little bit higher than 16. A sub 4 is 25. 25 is a little bit higher than 24. And A sub 5 is 33. So that's just a little higher than 32. Okay, and there's your graph. And what you can see actually in this case, if I were to graph it a little neater, they're all following on a straight line. Okay, so that's a linear growth rate in that recursively defined function. All right, so that's where we're going to stop today. As always, if you have any questions or concerns, don't hesitate to contact me. Good luck with your homework.